Good morning, students. Today we will start with Science 1, Chapter 4, Effects of Electric Current. Before we start with the topic, let us revise what we have learnt in Standard 9. What is electricity or electric current? The amount of charge flowing through a particular area in unit time is called electric current. It is denoted by the capital letter I and its unit is ampere or A. Then what is charge? Charge is nothing but the flow of electrons. We know that electrons always flow from the negative to the positive terminal. But conventionally when we are drawing the circuit diagram, we show the current flowing from positive to negative. Now look at the diagram that is given in front of us. There are three diagrams A, B and C. A is a living room scene where you can see the lamps and TV and fireplace etc. B is a rotating fan and C is an electric bell. Now the question that are asked to you is, what do you observe in the following picture? What do we see in the following picture? The above pictures or the following pictures show us the use and the effect of electric current. Next question is, which effect of electric current do you find? In the first one, what we are seeing is, it is an example of heating effect of electric current. We can see TV, we can see lamp, we can see electric fireplace. So it is a heating effect of electric current. The second one is rotating fan or moving fan. And the third one is an electric bell. Both of these are showing the magnetic effect of electric current. In this chapter, we will be learning about all these things in detail. Energy transfer in an electric circuit. Look at the given diagram. It's a circuit diagram. Let us revise all the things that's given over there. The plus sign or the bigger line shows the positive terminal. The negative sign and the smaller line shows the negative terminal. We know, just now we learned also, that electrons flow from negative to positive. But conventionally we show current I flowing from positive to negative. AB is the conducting wire, R is the resistance, A is the ammeter and V is the voltmeter. Ammeter calculates the current flowing, whereas voltmeter shows the potential difference. Now if you look at the circuit diagram, it's a complete diagram. Now in this particular diagram, the potential at A is higher than the potential at B, as the point A is connected to positive electrode of the cell and the point B is connected to the negative electrode at the terminal of the cell. Hence, electrons moves from the negative to the positive. So as the charge Q or the electrons are flowing from A to B, amount of work is being done, which is given by the equation W is equal to V into Q, where V is the potential difference across AB and Q is the amount of charge passing. Now from where does this energy come to do the work? That means we know whenever there is an amount of work is being done, there has to be an energy. Who is providing the energy? In this particular circuit, the source of energy is the cell or the battery shown over there. Now, if the charge Q flows from A to B in time t, that is the work is performed in time t, then during that particular time the energy VQ is given to the resistor R. What happens to this particular energy? That means the energy that is being given by the battery to the wire and going to the resistor, what is happening to this energy? This particular energy received by the resistor is converted into heat energy, and we see that slowly the temperature of the resistor increases. So in the example we saw that the energy received by the resistor is converted into heat energy. Now imagine that if in the circuit the resistor is replaced by a motor, then which form will the energy given by the cell get transformed into? In that case, the energy will be converted into mechanical energy. So in the first example, we saw that the electrical energy gets converted into heat energy. If it is there is a motor instead of a resistor, then the electrical energy will be getting converted into mechanical energy. So electricity can be converted into various other forms of energy. The next we see is a derivation of Joule's law. Now we know that power is equal to energy or work upon time. Now we saw that work is equal to V into Q. So therefore P becomes V into Q upon T. But again we know that Q upon T is equal to I, or I is equal to Q upon T. So the first equation becomes P is equal to V into I, where P is the power, V is the potential difference, and I is the current. Now during time t, the energy given by the cell to the resistor is equal to P into T. Now this energy is getting converted into heat, which can be denoted by capital H. Therefore, the heat becomes, or H is equal to P into T. We can substitute that and we get V into I into T. That is the second equation. Again here H is the heat, P is the power, T is the time, V is the potential difference, I is the current. According to Ohm's law, V is equal to I into R. Now, if you are substituting this in equation number, if you are substituting this in equation number 2, what do we get? We get that H is equal to V into V upon R into T, which is equal to V square into T upon R. How did we get this? We changed that equation, that is H was given to us V into I into T. Instead of that, we wrote V, instead of I, we wrote V upon R into T. And then we multiplied, we got equation number 4, which is equal to V square upon T upon R. Similarly, H is also can be written as, instead of V we can write IR, again instead of VI we can write IR upon R into T. Cancel R and R, what we get is I square RT, or in other words we get the equation H is equal to I square R into T. This is called as Joule's law of heating, where H is the amount of heat which is directly proportional to the square of the current, resistance and the time.